I'll also make a quick comment here, just preliminary to going on with this solution. The units of R over L, we didn't work out before, but the units of R over L are kilogram meter squared over coulomb squared seconds, that's R, divided by kilogram meter squared per coulomb, that's L, and that's per coulomb squared. And you can double check that. So the kilograms divide out, the coulomb squared divide out, the meter squared divide out. You're left with a second in the denominator, so the units of R over L are reciprocal seconds. So that e to the negative R over L, well, it actually should be R over 2L. Probably hard to read now. Makes sense because negative R over 2L has units of reciprocal seconds, time has units of seconds, so you have e to just a number, which is absolutely necessary. You can't have e raised to something with units. So now it's easily seen that your Q, the charge on the capacitor, whose derivative is the current, whose second derivative is what drives the voltage of the inductor, is equal to some Q naught, we'll say. We could use any constant here. I just used Q naught. Times e raised to, well, it's e to the mt. M is this, and we probably ought to multiply that by t, which I apparently neglected to do while I was saying this in class, although I don't think that confused anybody any more than they might have already been confused. I'll note that Richard was sitting there following all this along with the textbook, and he never said anything, which would be, you'd think he might. So I did check after class to check my notation against that of the textbook, because there are various ways to rearrange this, and it turns out that the textbook had it right. They did it the way I did it. Okay. Okay, so anyhow, you get two real solutions if this discriminant is positive, repeated real solutions if this discriminant is 0, and complex solutions if the discriminant is less than 0. And these solutions mimic right down the line the solutions that we got for the mechanical system, the harmonic oscillator with a drag coefficient. Okay, now looking at what this implies, let's just see where r squared over 4l squared minus 1 over lc is 0. We rearrange that, multiply it. I multiply through by common denominator, which will be 4l squared c, and we get r squared c minus 4l equals 0. L equals r squared c over 4. Okay, that's the transition of the behavior of the system from the solution where your discriminant is negative to the solution where your discriminant is positive. Transition from an oscillating behavior to a combination of exponential behaviors. Now, it then follows that r squared over 4l squared minus lc is greater than 0 when? Oh, well, if L is small enough, this is big enough. Uh-oh. Well, delay what I just said there, but this occurs if L is less than r squared c over 4. And I'm going to stop and check that, because I want to check this at every point and make sure that I'm not saying something really ignorant. Okay, if I look at this, it's really obvious. If L is big, that's going to make this negative. Okay, but that's going to make this small, so that would be positive. Now, I'm still seeing a contradiction here. Hang on, I'm going to reconcile this. Okay, I've verified it 3 ways. Yeah, you do have an L in the denominator here, which would make this small, but you have an L squared in the denominator here, which would make this much smaller, making this bigger and this relatively smaller. So you would have a positive if you have a small inductance, and that fits with what you would expect. If you don't have much inductance, then your coil maybe only has a loop or two. Maybe it has a small area. We didn't really talk about how area affects that because we haven't talked about inductors in detail. But intuitively, a small inductance wouldn't make much difference in the behavior of a circuit. And the behavior of the circuit, of course, we haven't solved the equation to see this, but if L is absent or is small, then the circuit pretty much behaves like an RC circuit with its exponential behavior, and there's no oscillatory behavior. The oscillatory behavior depends on having a large enough value of L. And of course, oscillatory behavior is what occurs when this expression is less than 0, making the square root imaginary. Okay, so if L is big enough, you have oscillatory behavior. If it's small, you have something very much like exponential behavior. Okay, so now there's our detail of the types of solutions. What I want to do is assume that L is greater than R squared C over 4, sufficient to give us oscillatory behavior, and we're going to drive the system, the circuit, with the source V naught sine of omega S t. Now I'm going to stop here and just draw a little picture, and there it is through the magic of stop action. We have a resistance here, an inductance here, a capacitance here, and a source voltage here. So that's what we're talking about. You should have a picture of that, taking notes as you view the videos in any case. So you should have that in bigger form as we saw it earlier. Okay, well, if that's the case, then without going through all the details, which we kind of went through last time with a mechanical system, it should be clear to you, especially since this is presumably something that you have just been over in differential equations course. We get Q equals e to the negative r over 2 LT, right there it is, and then plus or minus, well, this is imaginary, so we're going to have a cosine of omega t, a combination, linear combination of cosine of omega t, sine of omega t, with omega equal to the square root of r squared over 4 L squared minus 1 over LC. This thing, this being I should say omega equal to the magnitude of this, because of course this thing is an imaginary and omega is a real quantity. So, but in any case, there's our omega. And note again, if 1 over LC is small compared to this, this just comes out close to r over 2L. So it has a magnitude close to r over 2L, but that won't make the thing oscillate. That would result in a positive term here, and that's going to drive your two exponentials. So you might want to think through what happens in this case, which we're not talking about today. Okay, so we get omega equal this, and now we want to solve the non-homogeneous equation here, so we're going to use a trial solution. And a trial solution for a sine function, omega s is the angular frequency of the source as opposed to the omega that we get here. Okay, so the trial solution is going to be, and of course I left the s off of my omegas here, but the trial solution is going to be of this form. The only way a series of derivatives can give us a sine function is for each of the terms to be either a sine or a cosine function, or some combination thereof. So our particular solution is going to be C1 times the sine of omega st plus C2 times the cosine of omega st. And plugging that into the equation, and you're probably not going to be able to read that, but it's just the same thing we had here. We take the derivatives. I'm not going to write this out, but the second derivative of this is negative omega squared times just what we have here. So the second derivative is going to give us negative C1 omega squared times the sine, negative C2 omega squared times the cosine of omega st. And I'd better put those s's in there before I completely forget to do that. Okay, this is omega S. This is omega S. So is this. So is this. Okay. Now, that's what we get. And then Q prime is going to be what? It's going to be C1 omega S times the cosine of omega st minus C2 omega S times the sine of omega st. Again, this is extremely straightforward. So if we just write it down carefully, we're going to have it right. And I believe that gives us a C1 times R over L omega S times the cosine minus C2 times R over L times omega S times the sine. Of course, we have the factor R over L multiplied by what we get from the derivative. And then we just have the Q over C. So it's just this divided by C, this divided by C. We get that by just doing C1 divided by C and C2 divided by C times, respectively, the sine and the cosine of omega st. And that has to equal our V naught sine of omega st. And notice I've made this kind of a fancy C here just to make sure we distinguish it from other C's like these, or like just from these two C's. Not absolutely necessary to do that since we have subscripts in these, and this is lowercase and this is capital, but keep it as clear as we can. Okay, now we combine these equations and we simply take the terms that have signs on them. Sorry, just wanted to look at this, make sure I'd really done that right. We have a sign here, and a sign here. So we take those terms and collect them together, and we're going to set that equal to V naught sine of omega st. So the sine of omega st will go out of every one of those terms, and we're going to end up with this. Negative C1 omega S squared minus C2 R over L omega S plus C1 over capacitance C, and that should equal V naught. The cosine terms are going to have to add up to 0 because we have no cosine on this side. So we just get this term and this term, and this term, and we're going to have each of those times the cosine of omega st, but it's going to end up being equal to 0, so we can divide out the cosine of omega st. We might want to worry about the case where the cosine is 0 because it is once every cycle, but we don't really need to worry about that. Okay? If you wanted to explain that, ask. Just because we're talking about multiples of functions and not the actual values, but we can deal with that. So anyhow, we get this equation, and then we need to solve these equations for C1 and C2. We'll proceed to do that in the next video.